We're very happy to have Sudipta Sarkar from IITGandhinagar, and he's going to tell us about rotating black holes beyond the
Well, great. Let's start, and it's great to be here. I wish there was a campus which can beat, yeah, but I realize it's very difficult. Every time I hear, I feel jealous. Okay, anyway.
All the IITs beat TFR, right?
It's not the C, sir. I disagree. Okay, that's C. I mean, it's interesting. Anyway,
this is IITGandhinagar.
so this is our campus. Yeah, this is the central courtyard. You're welcome to visit us. I mean, just drop by us whenever you are around. You will enjoy it. So this is the work which I'm going to talk. This is with a couple of students. Rajesh is currently in John Hopkins at a postdoc after completing his first postdoc from ICTS. Was a PhD student from my group, and then Akash is now in VIT faculty. Nitesh is a student of Samved at the IIA. So these are collaborators who have contributed to this one. So before I go to the technical stuff, I want to flash this, quotation from Landau and Lifshitz. I'm sure all of you have read Landau and Lifshitz and appreciate this. I mean, it's typical Russian style. Okay, so I mean, those who started their physics, like I was the first generations in India who was born into Griffith. Okay? In our days before, there was no Griffith. Okay, we started like Panofsky Phillips. We started our BSc with Griffith. And then if we ask to read Landau, we can immediately figure it out the difference in style. Okay. So if you look up to Landau, every line contains physics. Okay. So my claim is there is one line which does not contain any physics. And this is one line. So where he says that it was established by Einstein and finally formulated by him in 1916 and represent probably the most beautiful of all existing physical. This is too non-Russian. So it means even Landau and Lifshitz is impressed by the beauty of general relativity. This is definitely true. The theory is not only beautiful, whenever we have challenged the theory with observations, and today we have tools to see various aspects of GR observations which I didn't have a few years ago. And it turns out somehow the nature chooses general relativity quite well. Okay. And the idea of general relativity, the basic idea is this, what if we can call Wheelerian dictum, which tells that matter tells spacetime how to curve, and then curved spacetime tells matter how to move. And this is like standard. Okay. And then the dynamics of general relativity is this Einstein-Hilbert action. In here, I think D4 is not a good idea. Okay. I mean, one could add DD. Okay. But there are the surface terms which you have to add in general relativity, and then you vary the action with respect to metric, and you get, of course, there is a matter action which I have not written. And then you get this famous Einstein's equations, which is geometry and matter. Note that this is a choice. I could have added anything I want, okay, but nevertheless it works. And this is the simplest choice, and it works splendidly. Both theoretically, it gives very beautiful theorems, and it also observationally is supported. Whatever we could have done today, somehow we cannot beat. Okay. I like to point out that the coupling of I have suppressed the C. There is a 1 by C to the power 4 here. But note that there is only G and C. Okay, there is nothing else. Unless you invoke lambda to be a new constant in your theory. Lambda will have a dimension from length. So what I meant to say is that there is no intrinsic scale in general relativity. You cannot make a scale out of G and C. Okay. You need H bar at some place. Okay. So in some sense, the general relativity does not distinguish between big and small. I won't use the word scaling with it because that has a different meaning. But one would like to understand, for example, there is no meaning of cosmological constant problem in classical GR. Because it's just a dimensionful constant. How do you compare it with what is small and what is large?
I've never thought about setting H bar and not including H bar, but you can't make something dimensionless.
Yes, exactly. That is the whole point. So therefore, lambda is just a constant with dimensions. Like I cannot say
that. You can scale by doing appropriate scaling.
You can always do that, but you always keep. And if you set lambda equal to 0, then this question does not arise. These equations, although look simple because the notations are simple,
of course, we just 1 time take the ratio of lambda.
You can always take lambda and g, but what I mean to say is that if I give you fundamental constant g and c, you cannot create a fundamental length scale out of it. So now suppose you measure lambda observation, you get some value, 10 to the minus 80. Okay. Now, can you say this is a small number?
Why not?
Why? Or with respect to what length scale it is small?
I mean, that's dimensionless.
No, Planck, you are not allowed to bring. Without, in classical general relativity, there is no scale. Right? With respect to it, you can say it's like capital G. You cannot, unless you compare with other interactions.
G and lambda, they have dimensionful constants.
Yes.
You can take the ratio to get a number, right?
Not without H bar. There is no H bar. Sorry.
I haven't done it myself. Okay, I'll have to do it.
That is why I'm emphasizing that it is classical. In my world, sometimes H bar is 0.
3 numbers that you needed to settle, right? Set units, we need a 4th.
Yeah.
So these equations are second order.
Right. Okay.
And-
Maybe they can be considered. Okay, never mind.
So these are second order equations and these are nonlinear partial differential equations. So we know that these are separated into constraints as well as the dynamical equations. And the constraints are elliptic equations and dynamical equations are hyperbolic equation, but you have to choose a foliation to separate the constraints and the foliation. So the equations are nonlinear, therefore it's very difficult to say something about the general nature of the solution. We don't know. There are only very few exact solutions are known in classical.
Right. Yeah. So can you explain what the elliptic and hyperbolic?
So think of an equation, a differential, so it's a second order differential equation. So you have the characteristics equation. The characteristics equation classifies a differential equation to 3 classes: elliptic differential equation, hyperbolic differential. So basically, the dictum is a time evolution equation. It is a hyperbolic differential equation. If it is a flow equation, it's mostly the elliptical equation. So this is represents if you have an Aij, del I, del j of that field, then the Aij, whether it's a positive definite matrix or not, that determine whether how the characteristic curves will look like. This is a standard theory of classification of differential equations.
Actually, I'm very sorry. Since you're going to be talking about extensions of GR, just to ask you, so the initial value problem is not so well posed if you typically include higher derivative.
Absolutely.
Right? At least it's much more subtle. So, what is your view that you should only allow for such extensions where it is well posed, or are you going to say?
So, if you asked me 5 years ago,
yeah,
I would have said that it seems general relativity and its extensions to love law could be the good choice for because these are quasi-linear equation. You will be able to invert it and write it in this Cauchy-Lewinsky form, and therefore the general theorems of classical differential equations will apply. But recently there are many illustrations and results which seems to suggest the Lovelock class may not be a well-defined class. Okay. One possible reason could be that one could show in Lovelock the fluctuations, particularly the speed of the fluctuations. So you can look at the general fluctuations and write it in spin 2 propagation degree of freedom and spin 0 propagating degree of freedom. In general relativity, the index of spin does not interfere with the speed. Everything moves on same line. But in Lovelock class, it turns out that the fields, the nature of the helicity of this field determines the light flow. Light flow depends on that. This is a lot of work. It started with classic work, but relativists. If that happens, you can show it induces pathologies in the initial value formalism. So there is
related to the fact that causality is violent.
I'll go to that part differently.
Just take the fastest.
So now what happens is that suppose you want your Cauchy delta surface to be space-like everywhere. If you make it space-like for one species of field, it may not become space-like for other species of field. That's the problem. It's a classic paper by this guy. What is his name? This Harvey, which has shown this. And then there is also a class of problems which I have to be very careful in saying that, because not that I have complete faith on this calculation. Okay, there may be a way to bypass it, but what has shown is that since in class of Lovelock class of theories, one could create what is called this different sign of this Shapiro time delay. So Shapiro-Timely, you can think of it that it has a particular signs if your all theories contains positive masses. But you can choose polarizations in like Gauss-Bonnet theory as explicit example. You can get any sign of the Shapiro mass, that's Shapiro-Timely. Then it's a bad thing. You can sometimes create a closed null curve without violating any energy conditions. But again, there are ifs and buts on this. Then there is a recent paper by a couple of guys. Aaron Hurd is one of the guys. Okay? What they did is that they look at this, what is called this quadratic gravities, which everybody, all of us will hate because they will have ghost, classical ghost. What it means is that the kinetic term will, the Hamiltonian is unbounded from it. But then it is shown that our intuition of this ghost, this basic idea is that your trajectories in phase space with ghost unbounded. Right? But if that's based on our idea of free theories, but this theory also have potentials. In that case, they have looked at some numerical evolution. It seems the trajectories are not diverging. Some of the potential is not allowing physical trajectories to go to the problematic part of the phase. So there are now numerical evidences that quadratic gravity may not be as bad as we have thought previously.
It would certainly be possible to quantize it in a.
Oh, no. Quantize, I am not even going into those directions. I'm talking about complete classical. Quantum theory, that itself, GR would give you trouble. So, others will be.
Quadratic gravity is quadratic input.
So, quadratic gravity is this nomenclature. The definition is R square plus RAB. So, in 4 dimensions, RABCD, you can always use Gauss-Bonnet to write. So, these are like, but these are not 100% pakka result. So, these are going on. Okay.
So even classically, there's this Ostrogradsky instability.
It's exactly what I'm talking about. That if you have more than one, so these are Q double. Let's say you have a Lagrangian of Q double.
Yeah.
Then what you can do? Your demand is that the Hamiltonian should be a generator of time translation.
Yeah.
If you demand that, you can show that the Hamiltonian will always have a term which is linear in momentum.
Yeah.
And then
And that's independent of being a free theory or anything.
so now
the
suppose you have potential to it.
Yeah.
If it is a linear in momentum, that means there are places in phase space where you will have this. So they have shown that once you include the potential, there is no trajectory which goes there. There's some.
Oh, so you can have some consistent
Exactly.
application.
But this is just numerical evidence. There is no theorem to prove it. Okay, so I should clarify this. Okay.
Sounds extremely unlikely it'll work. Thermodynamically, it will populate these very high.
I hope so, but if somehow the numerical evidence says a certain kind
Meaning
of
somebody.
that's the result I have.
But the claim is you can start with some nice data and you stay away.
There's data you'll stay away from.
That's the claim.
That's the claim. Yes. But these are again by classical evolution
Yeah.
equations. So that's all.
Thank you, and sorry for that.
No, this is something very interesting actually.
But presumably as effective field theories, the cutoff, then of course they would make sense. You only
Again, so it's like moving the horse
to that energy scale.
But not the ones with the costs, right?
Okay, not the ones with the ghosts.
Even with ghost, you can think of that. Okay, so
Unless
suppose
it's like a ghost at a very high scale.
so you say that the ghost has suppose you say alpha RAB, the ghost will have a mass proportional to the inverse of alpha. So you say that I only work up to that scale, so the ghost mass is away from all my coupling. That is it. But again, putting the horse ahead. Okay, so there are results still say that the gravitational DFT could be problematic.
Really?
Yeah. So there are recent there are results which says suppose you have extremal black holes.
Yeah.
And you look at certain high derivative operator, how it corrects the black hole.
Yeah.
You can show that even if there is no curvature singularities, or everywhere the solution remains perfectly valid, the tidal forces diverges. Kind of a mass inflation phenomenon near the horizon. It means the effects which you thought would be small, however small the effective corrections you add, need not be small. So
This is
these
like
are
this Horowitz
Horowitz,
effect.
yeah. But again, there are a lot of problems there because you have to choose certain modes. Those modes may have problems in itself. What we did is and they also it depends on what kind of perturbations you are adding to it. We tried something where things are well defined. It turns out that that serious divergence does not come. So gravitational EFT can have its own problem. So there are new results which seems to suggest.
Which is going back to the Riemann square term.
Riemann square. Okay.
Quadratic. That the leading propagator would have a ghost rate.
Yes, absolutely.
That was just bad.
That is a bad classically because you will have a wrong sign.
Yeah. That is just crazy, right? Those sound like crazy. So it's not like there's a propagator here and then another one there.
No, yeah. If you have it, so all these things, what I'm asking is that it's a GR plus something. So if you have a leading term in Arabic, it's like let's say conformal gravity.
Yeah.
It'll be a big problem.
So you really must go on, but actually your last comment was partly in the back of my mind because if you have a very fast rotating black hole close to extremal curve, I mean these extremals are always on the edge because
Absolutely.
inner and outer horizons come together. And so it'd be very interesting to hear your comments as we go along about.
Although I have not included that yet, but I can discuss it.
If you don't get to it, then in private. Thank you.
Please.
For the last statement that we said, the EFT might not be a good thing, but that just means that we can't take, it's the statement that we can't take the gravitational EFT and use it on some like extreme regions of like calculations where like for instance like an extremal black holes.
I would say that.
For instance, we can always take like the gravitational EFT and calculate let's say scattering amplitude.
Absolutely. Yes. For example, gravitational EFT works very well. For example, we don't see anything other than GR, which means the other terms are suppressed. Even very close to the Kerr black hole, the black hole shadow, it seems to suggest that the other terms are whatever they are. Either they're exactly zero or they are suppressed well below the scale at which we map. But there are extreme situations which seems these are not well defined. The expansion is not a well defined object. That's the statement.
For those situations, one should like either.
But if it happens in one situation, then the question is that is it generic? Is it a very special situation? Or these extremal black holes, are they part of any physical evolution? But then questions come. Okay. And then, okay, the non-linearity of course. And then the eventual equation becomes hyperbolic. You have to fix a gauge. Generally, we use harmonic coordinates, then things are simpler. And then there is a very, very famous result by Brohart, old result, which shows at least the local in time existence and uniqueness hold. At least you can say that in the neighborhood of the data, the solution exists. And
For Einstein's equation.
For Einstein. Everything is for Einstein. So, then given a smooth initial data on a space-like hypersurface that satisfies the constraints equation, there exists at least globally hyperbolic development. Development by definition means local development. This is a very famous result. I don't know the proof yet. I'm still trying to understand this. So there are a lot of theorems used. Okay, there's a modern version of the proofs which are very interesting. But then there are other beautiful results which shows, for example, the Minkowski space stability. So basically it shows that if you solve vacuum-Einstein's equation, Minkowski space is a solution. If you perturb around it, then you show that there is always geographically complete solutions and which decays back to the flat space. This decays back has to be careful. What it simply means is that in an instanton language is very easy to understand. It means there is no nearby instanton. There is nothing to decay in. So there is this famous result of Gross and Ferry, I think, the stability of flat space. Okay. So this is known as the.
So sorry, but I thought when I read this that Christopher et al.'s result isn't just classical.
There's a classical result, but there's an instanton way of understanding it. So I have not read this. This is some 200-page paper. Okay, I only know that. Okay, but the Gross and Ferry, it may not be Ferry, it may be somebody else. If I'm
There is the famous.
That's actually easier to understand.
That's certainly because they just look at
Instanton and.
But I would have thought the two are different, right? One is about
No, I think these are related to it because in the Lorentzian picture, these are like tunneling between geometries. So there is a classical. You can think of a what should I say the path integral. If you take the saddle point limit, then you can relate it to each other.
What would if small amount of data forms a black hole, would that be called a nonlinear instability of Minkowski space? I'm just trying to understand what it means.
Yes, I think so. Right.
So the point, I suppose, of this Christodoulou paper was that if you have a low energy, you also need high density. So that if you have low energy and density, it doesn't form a black hole.
Or in some sense, there is another result.
small amplitude.
Absolutely.
Small amplitude and
Small things remain small. That's the idea.
Yeah.
Or more technically speaking, you cannot form a trap space.
That's correct. Yeah, that's.
So if you start with the Minkowski space, somehow that does not happen. But if you start with, please.
No, it's very easy to understand. Suppose you've got an incoming shell. Okay. And if that shell is not so concentrated that suppose its size is bigger than its Schwarzschild radius,
It will never form.
then it comes and just goes through. Okay, if you've got the same amount of energy,
Why it goes through? I mean, at some point it will go inside in short.
it doesn't, because if the size of the shell itself
Yeah.
is bigger than the Schwarzschild.
But it's collapsing, right? It's collapsing.
It's collapsing, but some part has gone out.
No, but if you take it collapses, no. What you take it
Collapse.
collapsing, then you are taking that Minkowski space is not everywhere a solution.
It's just an ingoing shell. So let's say we're doing a free gravitons. Just an ingoing shell, just like an ingoing shell of scalars. It's got a certain size. Okay, and it comes in, it's got this size. This part is what would have been within the Schwarzschild radius of the whole thing. But the whole thing is this big.
No, but
But it's not that simple, I
It
think.
goes through.
No, it may not be that simple, sure.
Smaller and smaller.
It is that.
Because there are results. For example, the same distributive result exists. He looks at two gravitational waves interacting with each other, and he shows that in future there is a possibility of forming of the cap surfaces.
But this experiment I'm talking about is really very simple. If you just take the size of this thing, large compared to the size of the Schwarzschild black hole you form, you can just analyze these equations and perturbation. Okay. And show the leading order is just free.
Do you mean the shell has a thickness?
Yeah.
So that's
You start with a wave packet. The wave packet has a certain thickness, which is large compared to the Schwarzschild radius of the mass.
so it doesn't see.
Oh, the thickness is large.
Yeah.
I see.
You made it large. Okay. Now you send it in.
I mean, it could be the thickness is not large, right?
Then it will form a black hole.
Yeah, but this is not a high density constraint.
It is high density because
Because I have a big area also.
no, but it will become a high density.
It will become, right? But
Yeah.
initial
Initial.
data is rare.
So
So what is the theorem?
the criterion will.
Okay, complete it.
No, it's clear. I did these calculations with Shantanu in ADS.
Okay.
Completely sure of what I'm saying. Okay, so
What I mean to say is that so there are
It seems very reasonable.
and then there's a critical size of this shell.
Yeah.
Critical thickness of the shell. It's worded in that language. You know, there's some data.
Okay.
There's on one side you will form a black hole.
okay.
On the other side you will not form a black hole. But there is an open neighborhood of data for which black holes do not form. That is the theorem.
That is the
Data is mentioned in terms of density.
Density.
I mean, there's an
Initial conditions
paper
are-
which is very complicated.
Okay.
But for physicists, that's what it's in terms of the size of the shell.
And of course, there are singularity theorems which says that the gravitational collapse can form.
And sorry, shock tweak.
Choptic is a
Shock tweak is the transition between these.
the scaling.
When this thickness becomes critical size, when the black hole first forms, it forms with some critical exponents.
That's the topic.
Okay, and the fact that this is critical behavior tells you that there's like a phase transition in this phase space.
But this ADS calculations you did in lower dimensions or higher dimensions? In
5 dimensions.
Five.
And for dimensions where there are gravity.
Okay.
I mean, they're real time.
Yeah, not in lower dimensions. Right?
Not an ADS thing.
So, or interesting thing that we know that there is Schwarzschild solutions which does contain a curvature singularities, and there are the singularity theorems which say that you can evolve into the singularities by regular initial data. So basically, the global existence of smooth solutions cannot hold in care of. Okay. And therefore, the solution of Einstein's equation exterior to isolated mass remains one of the most physically most interesting things. We all are interested in solving Einstein's equation around. And then the first solution is, of course, the Schwarzschild solution, which is spherically symmetric, asymptotically flat vacuum solution of general relativity. And it is what we call event horizon at r equal to 2m, and it has all these characteristics. It's a null surface. It's a boundary of the past or future nullity. For that, you have to draw the Penrose diagram. It's a surface of infinite redshift. The killing vector is null. It's a killing horizon because time-like killing vector is null on the surface. Then there is this powerful viscous theorem, which implies that any spherically symmetric vacuum solution in GR is always static. So basically, if you put a T here, okay, you can always get it away. Then there's an opposite theorem in general relativity, which is called the uniqueness theorem, which is first started in Russell, but now a lot of people have contributed to it. It says that if you start with a static vacuum, asymptotically flat black hole solution of general relativity, it will imply that it is spherically symmetric. So spherically symmetric implies staticity, but in general relativity, staticity with all these modular assumptions also implies spherical symmetry. The only
I didn't know this result.
oh, this is a very famous result.
I'm so sorry. So, okay, let me just absorb it. You take asymptotically flat spacetime.
Static.
Take the, so just on a particular hypersurface, you take a static solution, what?
So, do you have a
I don't want to, sorry, to slow you down too much.
No, it's okay.
Just to understand the state.
So suppose you have a coordinate system in which the matrix can be written. I's are the three coordinates, pt square, plus some hij, x, I, x, t, dx, I, dx. This is a good coordinate to say that staticity has been imposed.
So you're not allowing matter in this statement?
In fact, also, but you can use electromagnetic matter also. The theorem has been generalized to electromagnetic.
So, the sun is a static solution.
Sun is a static solution. Sun is also not a black hole solution.
It's also
Black hole boundary condition is important.
So
You need V equal to 0 at some x.
okay.
The fact. So,
I see. So,
No hair theorem, basically.
no, this is not no hair theorem, sir. This is uniqueness theorem.
Okay, and
These are no hair theorem
they
means
listen to the script, say all they want.
No.
Basically, it's saying that you can't have stuff outside the black hole.
not no hair theorem. No hair theorem says that.
Okay, I withdraw the word. It's saying that you cannot have stuff outside the black hole. That's what I want to comment.
see, just understand, but it is vacuum, right? No matter.
But you can add electromagnetism. This has been generalized with electromagnetism also.
So some generalization, you that answer with enveloping factor going with zero sum.
You can show this is nothing but very Schwarzschild solution written in isotropic form.
So this is what is violated with these with charged matter in ADS. Right?
Absolutely. Yeah. And then
Charge
very
condensate
interesting.
outside the black hole is a violation.
violence.
So the hair out, the stuff outside, sitting in equilibrium.
But you can
Is what- this is what
you can
saying.
also violate it. You can also violate it if you violate general relativity, possibly, which we don't know.
And is there a analog for the stationary?
I will come back to it immediately. So the stationary. So let me first go to the next slide and give you the. No, this is important. So what it turns out, so this is first proven in 4 dimension. Okay, I will still confine myself to staticity. If you keep staticity, then you can show this theorem generalizes beyond 4 dimensions. There is no non-spherically symmetric static black hole, even in higher dimensions. You can show that this is a paper by first time Ida and Gibbons, where they show that the spherically symmetric, suitably generalized d-dimensional solution is a unique static black hole, even in higher dimensions. Now, this is important because this is not true for stationarity. Once you go beyond staticity, you can show that stationary black hole does not have unique solution. 5-dimensional black hole can have Myers-Briggs as well as ring. But the ring, so in stationary, you have this, the Casimir has 2 Casimirs because it's a SO4. Okay? That's 3, sorry, SO4. Yeah, the rotational group. And therefore, you can have 2 independent angular momentum directions. You can show that if you take J1 equal to J2, the ring collapses. There is no static black hole. So, stationarity, there are uniqueness theorem does not hold, but staticity, the uniqueness theorem holds. And the proof uses a very clever use of positive mass theorem. There's a d-dimensional proof. This theorem does not, at least the original one, does not require positive mass theorem. But if you go to higher dimension, we don't know any proof which is independent of the positive mass. So that is the biggest hurdle in generalizing this theorem beyond general relativity, because we don't know any proof of positive mass theorem, hardly any proof of positive mass theorem for non-GR theories. Okay, one has to be very careful.
So like Witten's work and so on.
That definitely uses GR.
Is just 4D GR? Or?
Okay, the Witten's proof requires 4-dimensional GR. The original proof by mathematician and Young earlier, that is GR, but that possibly because that uses its curvature identity, I believe they can be generalized to higher dimensions. But I am not 100% sure because there may be some other complicated math parts there. But Witten's proof definitely require, because you require the manifold, the spatial manifold to be 3 dimensions.
So do you think there's actually a loophole today which says that higher dimensional flat space may not be stable?
That
Just to ask.
I have to be very careful. That I don't know because
It
whether
doesn't
this
really-
paper
Is it-
can be generalized to this paper. Sorry, I don't know. I mean, I cannot give you just
Okay, no, you can't. But just to ask the question, my understanding, very shaky, was that it's the positive mass theorem which ultimately guarantees the stability
So
of.
in GR, I would be confident saying that positive mass theorem holds for all dimensions. But don't kill me if I turn out to be wrong in GR.
But just the fact that at least up to a certain
No, I'm not talking about observation. I'm talking about just
No, I'm saying up to a certain dimension, the fact that gravity is super symmetrizable tells you that's true.
That's what I was asking.
The
Is that
origin-
enough? Witten's
No, not really, because
What?
What is positive mass theorem?
The energy in GR is greater than zero.
the area of mass is positive. Yeah.
Global, just global.
So the original motivation for positive, even if you look at Witten's paper, the original motivation comes
So
from
asymptotically, let's say 10 dimensions. Type the fact that GR is a consistent truncation of 2B supergravity.
okay, this statement I do not agree, Shiraj. This has to be proven. I mean, this is a plausible. I'll tell you, if you look at Witten's paper, the motivation for Witten's paper comes because supergravity Hamiltonian is positive definite. And then he says, if I take H bar goes to zero limits, I would probably get. But the main point is that you have to show so that your spatial manifold, the Cauchy hypothesis you have to show that the Hamiltonian of the field you write is self-adjoint. Self-adjoint. Therefore, even generalizing Witten's theorem for black holes is non-trivial because there is an inner boundary. There is a generalization of Hawking's field. So you have to ensure that there are boundary conditions on fields. He uses these Dirac fields for which the Dirac Hamiltonian is self-adjoint with asymptotically flat boundary condition. So just because there is a H bar tends to zero limit, supergravity Hamiltonian will be so then up to 12 dimensions, right? How 11 dimension. But I'm not sure that it will automatically go through. One has to be very careful on this.
I was thinking just I'll live on the boundary. On the boundary, the ADI Hamiltonian is a square or something. So it's possible.
So then what you can do is that if you don't have boundaries, you can also do one thing. The same paper as this comment. Suppose you do not care about the black hole boundary, but you assume that the spacetime is Kruskal extendable.
Okay.
Then there is a hypothesis that goes from one side to the other end of the other universe. Okay. Then also you don't have inner boundary, but then you have to prove that all stationary static are all solutions of general relativity. There is a Kruskal-like extensions.
Okay.
With asymptotically flat balance, then I don't know how
We
to
would be extremely surprised if this was not true, right? Because it would say that.
I'll tell you in Gauss.
No, I agree with you. I'm just asking what is the status of the.
But on Gauss Bonnet, I am ready to take a bet. Gauss Bonnet. Okay, bet is not of a great bet, but reasonable bet. The reason is very simple.
Okay, bet, what is
That positive mass theorem may not be valid.
Sounds very reasonable.
Okay, so then. So that is because
Silence causality.
the negative sign of the. So there is another proof of positive mass theorem which is very interesting, which is Sorkin and Penrose, which uses the positive mass theorem from the geodesic, actually using Shapiro time delay. So it shows that if there is a wrong sign of the Shapiro-Mal time delay, you can show that there has to be some negative area mass. Okay. So by using geodesic shoots up to infinity and coming back. Okay. My belief is that theorem seems to suggest that Gauss-Bonnet will have a violation, at least for certain parameter space, but one has to work it out. Okay. That's the point.
What was your comment that she's very in dimension? It doesn't work.
You have gravity, which is classically a consistent truncation of a supersymmetric. Okay. In that supersymmetric theory, even classically at level of Poisson, the Hamiltonian is a square of an operator. Okay, so that operator is possible. Now the way out would be that you can start with a theory that has flat space as a boundary and create a spacetime that develops a new boundary. I suppose that would be the only way of this. But we don't expect a finite energy process to create a new asymptotic universe. So it sounds like extreme.
In fact, the original motivation of positive mass doing that in a Witten's way came from supergravity. The original comment is by Desert. So Desert is sometimes it's very unhappy. Sometimes there is no more. That the credit always goes to Witten. Okay, that's so social.
So in 3+1, Witten shows that thing.
Yeah,
you show it.
That's it. There the problem is that if you don't have three manifold, you have to introduce fermions. Okay, so he does it by showing fermion. Fermion is just a tools.
Yeah.
Okay, but then if you have the Cauchy data have more than 3 dimensions, I think there are topological classifications problem exists. So I think then many of this there could be holes, or then you have some new boundaries. So that has to be ensured.
But it's not enough to say one asymptotic boundary. I define the Hamiltonian and the supercharge is all at infinity. and that's good enough. It seemed from your description you actually need to define.
For example, if you have black hole, then you have inner boundary. They have to show that there exists a generic class of boundary condition for which the Dirac Hamiltonian is well defined.
His point will be you can call that your definition of the Hamiltonian, but it's not what you get by integrating fields
Absolutely.
in the boundary, because there's a second boundary.
Then you want it.
Right. So he wants for this definition to show positive.
But that's the trick within users.
Maybe if you can show it for me.
So that it is obvious. It's
Okay, go. I'm so sorry, please excuse me.
No. Okay. Of course. So this is a very important thing to understand, that there is no static black hole. Yeah, please.
Said that static will imply that it is Schwarzschild, but then what about spherical symmetry? That is also
No. What happens is that why Schwarzschild, I mean, static will imply spherically symmetric, and the spherically symmetric solution is Schwarzschild.
no, but then so that bound specified. What if that hypersurface form?
Very good question. So what you show is that at the end of the proof goes like this. Okay, that proof itself is a beautiful proof. Okay, the best reference is this black hole uniqueness book by Hustler. Please look at it. But I'll tell you what happens. Ultimately, what you show is that
What was, if you're sketching up?
this proved that all static black holes are spherical symmetry. How do you arrive at spherical symmetry? You can show that. So there are this, think of space-time. So think of co-dimension two surfaces, which are like kind of r equal to constant, t equal to constant surface. Of course, there is no r, but these are co-dimension to compact surfaces. What you show, the extrinsic curvature of this co-dimension two surfaces are proportional to its intrinsic matrix. This is proven. Okay. Once you prove that, you can show by a theorem, again go back to Kobayashian thing, okay? You can show this is a necessary and sufficient condition, what is called a rigidity and spherical symmetry. Once you have it in one surface, you can create a spherically symmetric bound. This is the way, and then you know that the only solution asymptotically flat, spherical symmetry everywhere is. This is how the proof works. There are other.
Suppose you have charged scalar fields. Will the proof work with and Maxwell? Einstein Maxwell with the charge scalar.
Einstein, Maxwell, and charged scalar fields.
Charge scalar fields with charges that allow it to violate the super.
I have to I can't give you an answer immediately. I hope it does, because it seems like a nice matter field. It does not have any positivity being clear. So
I was thinking that if you are in the regime where superradiance sets in, there's more chance that something could go funny.
Yeah, could be. No, there is no superradiance here. It's a static.
Static, but there's charged superradiance.
Okay, charged superradiance. Okay, possible. But in that sense, we know that in that regime, there's a violation of energy conditions, right? Superradiance sets in that TAB has some. I think the superradiance you can show that there will be some violation of energy condition in that regime. No?
No. And superradiance happens in ADS space all the time without training.
Yeah, but that's from if there's you mean the reflection from the boundaries. There's kind of thing.
No, the superradiance happens at the horizon.
Oh,
then it reflects at the boundary. But
I will think. I can't give you a direct answer. I have to think. Okay. And then, of course, there is a rotating generalization of Schwarzschild metric. And if you're interested in history, please look at this. Is the paper which I found recently. I didn't know that it existed. It's a very nice history of Kerr metric. I will not go into the history. So basically, the GR guys developed.
There are these boson star solutions.
Okay, yes, there is boson star solution.
Presume other charged boson star solutions?
Yes, I think I have seen in literature.
Right. So I suppose what I'm asking is, could you imagine putting, even in the case that the superradiance bound is violated, put a black hole in the middle of a charge too?
Okay, I understand what it
This
is.
is roughly.
So the GR guys understood there is one way to classify the solutions of general relativity using what is called the eigenvalues of the conformal tensor. And then there is another theorem called Goldman and Shaxter, which basically says that certain class of null geodesics are allowed. What kind of, and if you use those null geodesics, you can simplify the metric, you can integrate dimensional equations. But then you have this famous Kerr solution, which is what we call the rotating generalization of general relativity, where A is the angular momentum, A goes to 0, it goes back to Schwarzschild solution. Note that the curve is written in a very special coordinate. Okay, and this is what we call Boyle linguistic coordinate. And in this coordinate, there is only one cross term, GT5. There is no other cross term. In principle, there is no reason for there should be more than only one cross term. We could have had RTTR. But the idea is that there exists a coordinate system, at least one, in which I can write down the mid-curve metric. In a way, there is only one cross term, and this has important consequences. Okay, see,
This follows just
from the Einstein's equations. Okay, but there are consequences of this, observational as well as theoretical consequences.
So this fact that there's only one crossover is the theorem.
I'll tell you the theorem. Okay, this is true only in general relativity. Okay.
So backing up one side. See, we talked about stability of asymptotic Minkowski space, and there was this question of positive energy. But positive energy does not by itself imply stability in the way you define it. Right?
Agreed.
Backwards.
Because you have to go beyond.
Because it could be that any open neighborhood of data.
Let's say ADS is a counterexample.
Exactly.
ADS is a counterexample.
So
why is it? What do you? I thought you meant that it could have been that you form a black hole.
Yes.
Space defined that
that there is no open neighborhood of data.
which doesn't
Does
form.
not form.
But here in ADS case, ADS
I mean, it bounces back and
bounces
forth.
back. Non-linearly, you can form ADS. This is a famous ADS instance. Yeah. Which is
It's
not-
very versatile.
no, not the bomb.
The bomb, it doesn't amplify. Just keep
Yeah,
going till it
keep
falls.
going, coming back, and at some point,
Or whoever.
I do remember.
And it is thermodynamics in some sense. Right? Because if you put a certain amount of energy, your highest entropy solution is to put that energy into a
Yes.
small black hole. It shouldn't do that.
But it requires boundary conditions.
Yeah, I agree.
So it's to be careful.
Small black hole, even classically, you would still form.
But you need reflecting boundary conditions.
That would be your guess. Like one of two things will happen. There's a blank instability. So one of
Why
two
do you call
things
it
will
blank instability?
happen. I'm saying that one of two things will happen. Classical field theories don't have good thermodynamics.
Agreed. Yeah.
So energy keeps running into the
Yeah.
UV. So that will eventually happen. Or a black hole will form.
You mean either you go to the Planck scale or the horizon will curve?
Yeah, one of the two you should expect because there's no good thermodynamics for classical theory. So either quantum mechanics will kick in or black hole.
Or at some point the classical theory breaks down or horizon will
Prove quantum effects. And
at some point
If
it
you
will.
don't include quantum effects, then you should expect that it goes into a singularity.
Singularity.
Very short distance. Because things just keep going in deeper and deeper and deeper. You might expect black holes will.
Because this is ADS space is a good example.
Okay, and once you include the epsilon interaction, whatever. Of course, free theory is fine.
No, free theory you will not talk. You have to start with something. So
But then the interesting question is what are the time scales?
in ADS it turns out that you can get it
Very
if you
fast,
have.
yeah.
Okay, so what are the properties of curvatric? Obviously, it is not static. You cannot write a global coordinate system in which you can get rid of this cross term. Of course, you can write it tetrad at a single point. You can always write it as a tetrad in a but it is not static. So, in some sense, it's not invariant under the time universal T2 minus T. Then it is stationary. It does not explicitly depend on time. There is a time-like Kerr vector. That's the assumption I start. It is accessible. That's again not the assumption. I started with a stationary solution, black hole solution. It turns out the solution I'll get does not depend on a coordinate phi, such that the killing vectors for to phi can be identified with the Poincare killing vector for rotational symmetry at infinity. So that's the definition of axisymmetry. Okay, this is again consequence. It is invariant under the simultaneous inversion of T and phi. So the only cross term between T is dt d phi. So you take to phi to minus phi, T to minus T, the metric does not change. The metric is asymptotically flat, admits two killing vectors, as I told you. The metric represent please.
What is the consequence of the fourth?
Can you give me some time? I'll come back to it. One of the consequences would be what I call, there's only one cross component. This is what is called a circularity. I'll come back to it. You can clearly see, just because I'll be always able to write in Boyle linguistic coordinate only one cross term. So this is G phi T d phi dt. Then it is automatically clear phi to minus phi, T to minus T is a symmetry.
This TP symmetry.
T phi symmetry. Boyle call it T phi. We call
It's not
it
parity, right? That's that.
we call it T phi symmetry.
But
Why-
I still don't think this is TP symmetry.
But why would call it a TP symmetry? Where is parity in it?
Yeah, parity. Right? Flipping the sign of phi is parity not solution.
Okay, in coordinate, flipping the sign of coordinates in that sense.
Yeah.
You can say. But generally, the term used in GR is T5 symmetry. That's all. Sorry. Okay. And then, of course, you know that there are, and this represents a rotating black hole. How do we know it's represented a rotating black hole? Because it contains very interesting observer called JAMOs, which are zero angular momentum but possess an angular velocity. Okay. And when you bring the JAMOs to the close to the horizon, they start co-rotating with the black hole itself. Okay. And that you define as the velocity of the horizon. And this is dragging a combinatorial frame. It is not a theory. We have seen it in gravity probe experiment.
Okay, tell me later. You've seen it experiment?
Yeah, so this gravity probe satellite with the gyroscope has seen this been local inertial frame rotating.
Explain the Samo again.
So you start, so suppose there is no GT5, then zero angular momentum will imply zero velocity, angular velocity.
Zero angular momentum of what?
Of a particle, test particle coming from infinity. Now, because you have a T5 component, if you write down, you get zero angular momentum observer is possible, still with the angular velocity.
By observer, you mean particle?
Particle, a geodesic.
Okay. Okay.
At infinity. Okay. So then you can show that it can have angular velocity g minus T5. So this minus sign ensures that the angular momentum goes to zero. But because of this GT5 existence, it can have a zero angular velocity.
And how is angular velocity defined?
So angular velocity is defined as omega, which is like I forgot the original how do you? It's like typical Newtonian way from the geodesic phi. Yes, phi dot.
Phi dot. Very far away, it's just phi dot.
That's it. At infinity is phi dot, but when we come close to
constant
it,
phi.
it's constant.
Non-zero zero angular moment doesn't stay.
So you start it radially, but then it start rotating on it.
Yeah, and this is roughly because GT phi is like gauge field for this for angular velocity.
It's what we call the precision of.
Yeah, so phi dot.
What do you call it, a gauge field? I mean, you don't use this word, so I'm just asking.
Because he's compactifying on the phi.
Something phi dot minus 8.
It's a different word.
So you said phi dot to 0 or a phi.
Okay. So this interesting property is called the dragging of inertia. Then Kerr also has what is called an ergosphere. What is ergosphere? We can consider static observers in Kerr spacetime, and such static observer has a core velocity proportional to the Killing vector U alpha, T alpha. You can show that the static observer cannot exist everywhere in Kerr. What I mean to say that static observers are not time-like everywhere in Kerr. Okay, even outside the horizon, and there is a limit which is called GTT equal to 0, which if you solve it, will get this solution. And then inside this solution surface, static observers are space-like. Outside this surface, the static observers are time-like. So basically, you can have static really in a rocket. Okay, only up to a certain extent in the Kerr spacetime. Beyond the point, you cannot go static. You can still remain constant distance from the horizon by co-rotating with the black hole. Yeah. Okay, that's a co-rotating observer.
Can I ask you a very fair question? Sorry, which is observational, which is, can accreting disks get past the ergosphere? If you tell me later, I'm just curious.
I can tell you something that there are, I don't know what accreting is.
Okay. But just, it
could be very close. I don't know how far, but there are, recently there are proposals to see ergosphere using shadow. The idea is that you can have jets originating, and if you trace back the jets, they cut the ergosphere at some point. Okay, because ergosphere plays a very important role in creating jets. Because one of the Penrose process, not the particle Penrose process, the so-called field Penrose process, or the seems to play an important role in ergosphere. These are very dirty astrophysics is going on.
So, Sandeep, is your question that does the ISCO lie beyond the
ISCO? Okay.
The ISCO probably does lie beyond.
Stick same you can, but ISCO you
the smallest stable.
Last stable orbit. Right. But that's for time-like observer. What is the last stable orbit?
What was your question then?
Well, I was just wondering, that's why it's a very unfair question, but whether once you include all the horrible stuff, astro that goes into these disks, whether you can.
I don't know about accretion.
And stay there.
Yeah, and stay there.
Accretion disk, I don't know, but definitely for shadow,
you can have interesting dynamics.
And then the question is that you can choose a frequency. In that frequency of observation, the accretion disk almost become vanished, become transferred in that frequency. But
is there an orbit that it goes into, a stable orbit that goes into the
stable orbit goes into the what?
Ergosphere? That's one part.
Yeah, that's a better way to go
Let's
precisely.
see. So ergosphere, the maximum extent of the ergosphere will be what? If you take theta equal to 0, theta equal to 90 degree, the maximum extent is 2m. So then 6m is far out. So
But these formulae also change with once you include your rotation.
no, this is with rotation, right? I put
No.
theta equal to
But
90
6m
degree.
is only true for Schwarzschild.
No, 6m is also true for Schwarzschild. I want us to actually put the formula and see that there is a path which goes and comes.
Comes out. Yeah, okay, that's a better way to ask. Yeah.
I have to look at the formula.
Okay.
So, but what important thing is that it's not a null surface.
Yeah.
Ergosphere is a time-like surface. Okay, that's important. So the killing vector is not normal at ergosphere. Okay.
One question about this, what does shadow,
Okay, that I will bypass that because that's a separate talk. Okay, because I have to explain so many things. And the problem is that, so let me make one comment which is important. That shadow is not only described by the contour of the null geodesy, because there are also matter there. So what we see there is just not like the contour, because you have to integrate through the accretion disk, and what you are looking at is an amalgamation of all those things. So
I was asking what is a shadow?
so in some sense, there is a. I will come back to it because there is a.
If you've got light behind the black hole, where do you not, in what angular region do you not see?
So spherical black hole is very ideal. So the idea is that you should see a 3m,
Right.
but you actually see a 3 root 2m.
Right.
That root 2 come because the light is moving in a curved spacetime instead of flat spacetime. That's all.
Yeah.
But once you include rotation, things are complicated. Okay, I must emphasize that the horizon rotates rigidly with the angular velocity omega. So what it means is that this angular velocity is independent of theta. Again, it's an important thing to remember. That all this happens by the field equation somehow implies this.
Just curious,
Yeah,
like
please.
for Kerr, is it like a Spoda thing?
So Kerr, what happens is that it has a plane, theta equal to pi by 2. The closed null geodesics only exist in that plane.
Right.
Then there are spherical null geodesics which are constant r, but its theta changes. There is a region between which those spherical null geodesics exist. What shadow is that you take your line of sight, you go through it, all these things, and project it in the plane, cosmic plane. Then you see how each line will contour will look, and that is what is we call the shadow. Now the problem is that you have to go through with the accretion disk also, then you have to
Mess up. This is a great mess.
But one point is that there are frequencies. This is the main point, that within the IR band where you observe, for which the accretion disks may not contribute good. So may vary because these are opaque to those frequencies or transparent to those frequencies. So therefore, the contour structure of light rays will be equally visible to you. That is why one could see in next generation EHT, there is a possibility of seeing the ergosphere. Okay. We have not seen ergosphere. Good. And this is what I just wanted to. So if you write down the effective potential of a null particle in Schwarzschild, you will see that there exists a maxima. This is where the r equal to 3m, and this is where a unstable circular orbit for the null particle exists, spatially circular, obviously. Okay. It's unstable because this is the maximum. And if you look at Kerr, unlike spherical symmetric case, Kerr has a light ring only on the equatorial plane because that has a theta2 minus theta symmetry. And this is the solution of the same r equal to constant solution on the radial, the closed solution. So the plus and minus is basically two signs of the angular momentum, whether this is called rotate and what is the opposite of rotate? I forgot to think. Correct, rotating and counter rotating. Again, the angular momentum in the co-rotating with the black hole and opposite side.
So at A equals M, this becomes what?
A equal to M, it actually does one r minus goes to the horizon, other become equal to the same of the Schwarzschild thing. It's a very interesting feature.
That's the extreme.
Extreme one. So this, you can show that this one will go to the horizon. So that light ring forms the boundary of the photon region. So this is only on the equatorial plane. Of the equatorial plane, you will have geodesics which can move in the theta directions also. Okay. So It plays a central role in determining black hole shadow, and not only that, such existence of such unstable light rings plays also important role in the quasi-normal mode of current, because these are the potential, the structure of the potential is determined by this light ring. So of course, if you look at the perturbations, the potential matters. So therefore, they play an important role in the quasi-normal modes.
That light ring is outside of the question.
Yes, I'll tell you so. So that I will going to prove that light ring, there will be always a light ring outside the sphere. Always, at least. Then the Kerr has also very interesting property. It has two conserved quantity, which is obvious, energy and angular because of killing vector. But if you look at this geodesic structure, that's a time geodesic structure, you would have thought that Hamiltonian principal functions will be in this position because there's only two integral killing vectors, and there's nothing here. They will not be able to separate the equations into two first order differential equations. It turns out that's not the case. Somehow there is a conserved quantity which is obviously conserved because these are all conserved. But this Q, existence of this Carter constants allows you to integrate R and theta separately. So you can separate out R and theta equations. These have become first order equation, and you can integrate. That is because Kerr has a very famous what is called a killing tensors.
Is there an analog of this in higher than 4 dimensions?
Yes, I think so, but there are some results that are higher than 4 dimensions. The supergravity solutions has this killing nanotensor. So these are all very, very interesting accidents in some sense, which Kerr metric has, which we have not started. So these are the list.
At least this is just an accident. You can't understand its structure somehow.
No, you can. We know that why. There are certain parts we know that why. So this particular, we don't have much of an understanding.
Some symmetry type explanation or something like that. Something that there is some underlying.
Killing tensor is not really a symmetry. It's integrability conditions. I don't know. I mean, that if there is a bigger way to go to a higher space where.
Yeah.
Since you're asking this question, does it mean that it's not relevant from the CFT side? Or if you...
Well, I will come back to CFT maybe in the last one.
So, you see, the Schwarzschild black holes obviously have this problem.
No, that's almost obvious.
And yet, the quasi-normal modes are not well understood from the series. Okay, so this is a.
But in Schwarzschild, what do you mean by quasi-normal modes? In Schwarzschild, at infinity, it's a flat, asymptotically flat. So
what I was doing is putting Schwarzschild in. Yes, I think that's the spectrum.
Oh, sorry.
Okay, and then there's a complicated spectrum of Schwarzschild, quasi-normal modes of Schwarzschild in areas. And there's nothing to say about it from the safety side.
But at least you can show the fundamental
hydrodynamic
ones.
Except for that.
Yeah,
Nothing
concrete. It sounds reasonable.
In fact, I'm going to make some comment on those modes on asymptotic ADS condition.
I just thought that since there's a conserved quantity, if there is a conserved quantity in gravity, then maybe that can correspond to some conserved quantity.
I understand your question.
Okay, you are
thinking it's probably not conserved, but maybe something to say. That is structure.
So what happens is that if you write down the radial and theta equations, you can show that theta equation, radial equation becomes theta dependence, radial dependence equal to Q.
Does this persist in ADS? First question.
That I have to look at it. We don't look at ADS immediately, to be honest. Okay. So these are the list of the interesting thing. The Boyle linguistic coordinate, there is only one cross. Second, Kerr is a third conserved quantity, Carter constant, and Hamilton-Jacobi equation is separable. What is interesting is that box phi equation is also separable.
Yeah, I was about to say, it's related, right? There is an extra.
Okay, but you can have solutions. By hand, you can write the solution for which Hamilton-Jacobi is separable, box is not. So you can come up now, the Ramesh and Prashant have written down, just by hand, class of solutions, extensions to Kerr metric, for which I think both Hamilton-Jacobi and box phi equal to 0, both are separable. You can even ask, okay, if Dirac equation is separable, I think then there's only very few, maybe on Kerr is the only one we know, because Dirac equation is also separable in Kerr. I have to look at it. So you can write down the general class of solutions for which it's very interesting mathematical questions.
But one doesn't imply the other.
Then the spacetime is axisymmetric as well as rigid. There is no differential rotation of the horizon. There is an ergosphere outside the horizon. There is a light ring outside the horizon. Okay.
So given that we have a third conserved quantity, can that result in modification of the first law related to curves?
No, this conserved quantity is not like a Noether charge at infinity. This is conserved because of the other conserved quantities. It does not imply the existence of a new killing vector. So there is not really a Noether charge at infinity.
I'm sorry, you must go on, but just from the properties of horizons or the laws of horizon behavior, you can't prove that if it's a killing horizon, they can't be differentials.
No, just from the definition of killing horizon you can. But there is something called
In hypersurface, you can't have differential rotation of the horizon.
What does differential mean?
but the omega depending on theta. You cannot. You can only say omega. Okay, the way it proves all these proofs goes and you have to use the field equation at some point. Except this part, that there is an ergosphere outside the horizon, there is a light ring. This part can be extended without using the field equation.
But you have to use the Einstein field.
Einstein field equation or the corresponding. I'll say about what happens if you use EFT. Now, the first one, let us understand the first line. The first line comes from a theorem in GR. Okay, again, I will not go into more details, but let's see. A general stationary spacetime will only have a time-like element by definition. Spacetime is axisymmetric, it admits a space-like Killing vector which has closed orbit and integral curves generate rotations around the axis. Okay, which is like a standard notion of del phi. And a stationary as well as axisymmetric spacetime is these two Killing vectors will commute. That's the beginning. Then you would be able, always be able to write the metric into this form. 3 and 2 are not this T and phi. Okay. You'll be always able to write down the metric into this. Then you can define a further subclass of spacetime, call them circular spacetime, where you say that this is a subclass of stationary and axisymmetric spacetime. In addition to this symmetries, there always exists a family of two surfaces which are everywhere orthogonal to the surface of transitivity. What is surface of transitivity? These are generated by this T and phi. So basically, the idea is T phi gives you two surfaces. There is always a surface of another two surfaces which are orthogonal to it. So basically, you will always be able to write down the metric into 2 cross 2 form. So if you could able to write down, then you can show that you can always choose at least one coordinate system in which the cross term will vanish. And this is what we call the Boyle linguistic coordinate for curve. This is a very subclass. Again, let me emphasize, in general, stationary axisymmetry does not mean it. It's a subclass which are imposing by hand. Then you go to World General Relativity book, 7th chapter, it will give you this theorem. So this is directly copy pasted from that book. Okay. With no shape. Okay. It says that suppose these two are the commuting Killing vectors. One is, let's say, time, other is phi. Okay. And then these are written in a strange notation. These are nothing but wedge products. So if you see it in a different way. So it says that at these two vanishes at least one point in the spacetime. This is given. And these two conditions vanishes everywhere in the spacetime. Again?
What are those? Can you?
So this is
no, we get it.
So this is okay.
Yeah.
It's difficult to interpret, but so what you are looking, at integrity conditions of two planes perpendicular other two planes. There will be, what is this called? There's this integrity condition has a name. Basically, in some sense,
not related to Frobenius.
Oh yes, these are excellent. So these are Frobenius theorem conditions, just generalized to spacetime which has a Ricci scalar. So therefore, the wedge products are coming. Nice. Okay, these are like omega ABCD is equal to 0. That's all.
Nice.
How are those wedge products?
These are antisymmetric, totally antisymmetric.
Twice.
Huh?
Xi appears twice. So.
Yeah. So what? I mean, it's not really fully, but there is a derivative acting on Xi.
Yes.
Fully anti. So this you can think of as a dual of the wedge. Okay.
Integrable means that there are two coordinates which will be constant on this plane.
Constant on the plane. Therefore, you can choose a one r direction, one theta direction when you don't. That's
so it's a usual kind of thing, right? It's just
absolutely. But
no.
But point is that you can identify general conditions.
Yeah.
Now, suppose I live in an asymptotically flat universe, that asymptotically flat black hole, which has an axis. The definition of the axis is that is where the psi vanishes. Motivation is that think of sine square theta vanishes on the axis. This is where asymptotic flatness is required. To prove that the axis exists, you require asymptotic flatness. This is what these theorems are not generalized to ADS or TS boundary conditions. Okay. So therefore, in a asymptotically flat black hole case or asymptotically flat GR stationary accessibility solution, will be true at least on the axis. If it is a vacuum solution of general relativity, this is identical because RAV is 0. So therefore, these two conditions holds true for any vacuum solution of general relativity, which is asymptotically flat, stationary, and accessible. So if I give you stationary accessibility vacuum solution, these conditions are true, and therefore that solution will be circular.
It's interesting the condition involves Ricci, not Riemann. Because you might have thought
Riemann would be difficult, right?
would be difficult, but you might have thought that is what would come about in some,
But it's not a geodesic equation, right? A geodesic deviation equation.
I was thinking that, you can't put.
Think of the Raychaudhuri equation also is a Ricci tensor which comes, not the Riemann tensor.
That's true. I was thinking that you can't set, two.
You mean the EA path?
Yeah, this path, that
what is
path
it called? The parallel transport problem.
This and this to make coordinates. The obstruction to that is like.
But the problem is that then you will make the only solution would be like flat spacetime that you don't want.
Yeah.
So since these are true in general relativity, therefore any vacuum axisymmetric asymptotically flat spacetime in general, we don't even have to have a black hole. Okay, must be circular. That means there will be only one cross term. Okay. And Kerr is obviously such solution. This is why in Kerr, you can always choose one linguistic coordinate in which there is only one cross term. In fact, you can show that if it is a black hole, the zeroth law, the constancy of surface gravity, has almost become a triviality. You can prove it without using Einstein's equation. The circular black holes will have constant surface gravity. So that means this condition holds true. The circularity is the definition, and you will always be able to choose a coordinate system in which there is only one cross term.
Usually the proof of constancy of surface gravity is
very difficult. Yes.
Surprisingly.
But somehow, if you have a circular black hole, it's a triviality that you can show that that particular component. In fact, you can see, if you remember, R psi is the particular component which determines the variation of the surface gravity across from generator to generator. Okay. So
that is constant along generators probably obvious.
That is the constant on. See, you can go from time directions. Yeah. These are killing directions.
I see, but usually Shiraz says it's
across the generator.
Across the generator is the one.
And that is determined by this R psi. R psi is the part. So basically, how kappa goes from one generator to other generator is the non-triviality. But along the generator, the killing equations will tell you.
Yeah, exactly. But there it's non-trivial.
Yeah, so therefore, the circularities are very interesting conditions. Now, there comes a very, very more interesting thing. This is a paper by Nikutes, okay, and his student Z. So their claim is that if I add a EFT of gravity, that means I add all possible higher curvature terms, no non-minimal coupling or anything, okay, simple higher curvature terms. Then I would modify my Einstein's equations into this. Look how I am writing this. I'm keeping an alpha outside. Okay. So that's the notation I'm following there. So this will have MAB will have 0th order term, alpha order term. So that alpha order term will become alpha squared. Okay. What this theorem shows that they show that the circularity condition is something like this. Okay, again, this is this zeta is nothing but either time-like killing vector or the space-like killing vector. Eta is the vector perpendicular to the plane to it. There's some mathematical condition which will ensure the circularity. This is basically massaging these two conditions into one. Okay. What they show is that if you start with the GR solution, which is circular, and you want to see what is the corrections to the GR solution, you can show if you start with a circular condition and go up to order alpha, the violation of circularity will be alpha square. And you can go along like that. This is, remarkable result. Okay.
And you can go order by order?
Order by order. You can go up to order alpha to the power n. The circularity violations will always you can manage. So basically what happens is that this m, the 0th order term of m, you can always set to 0.
And circularity was meeting the condition of Wall's theorem?
Was, yes.
So this psi and n are d by d phi and d by dt or
no, zeta is either d by d phi when for values of eta z equal to 3 and 4, it is either d phi or d dt, and this is a vector perpendicular. Think of del R and del.
But in Gauss-Bonnet gravity for a 5-dimensional,
Doesn't matter.
but if I wanted not to do order by order,
Oh, then you'll be okay.
then is it true?
It is true if you start with the Einstein branch and expand everything. So if you have an Einstein branch, this is definitely true because you will be able to expand.
So it's true on that branch.
On that branch,
and an
with,
exact statement.
with alpha being Keller expandable.
Yeah.
Then it is true. So this is, I find it remarkable. So what it's saying is that any higher curvature corrections to spacetime, whatever they are, must be circular, at least in the EFT sense. Okay. And this is a very, very important result. So what it tells you that, so the assumptions are matrix is the only degree of freedom. Asymptotic flatness is a major assumption. Without the asymptotic flatness, this result cannot be generalized. I'm not saying that it will not hold, but honestly, what
Is this a theorem for vacuum solution?
no. In fact, it is valid even without vacuum solution. On matter, you have to impose certain conditions. With vacuum, it is trivially true because TAB is zero. So then it turns out you can use this paper to set up a test for GR, or rather test for geometry. Okay, not only GR.
Remind me, I'm getting lost. So the circularity implied what?
Circularity implies two plane perpendicular to two plane, which would imply there exists a coordinate system on which there is only one cross component, GT5.
And that is important for what reason?
Because this will imply T2 minus T and phi2 minus phi symmetry, which will imply, as I'm going to tell you, certain structure of the quasi-normal modes, which can be tested.
Nice.
But that's for when we have gravitational wave observation in our hand. But even for a theorist who try to solve field equations, this will be enormous simplification of the number of equations you have if you only have to work with circular patterns.
Nice.
Even then, we don't have exact solution, but it's an enormous simplification because you are saying that I can always choose coordinate system with certain coordinates, certain components I can set to zero.
Okay. And does it also imply the separation of these equations into theta?
No, it does not. Circularity does not imply that. Circularity one does not imply Carter constant, but Carter constant will imply circularity. But it's not like that.
Fine. So you're saying that one property, the circularity is just structure. It doesn't depend on details.
Other is what we are trying to prove.
Yeah.
That
Okay.
is the Carter constant is also can be extended order by order into the effective filter. That's a very important question because that will directly gives you observational consequences. So what we saw is that, okay.
Just to ask, that seems very important, but more practically, just find order by order in alpha the geodesics by correcting starting from.
But how do you know the space-time?
No, I mean, I thought the structural argument was, okay, you correct the space-time to order alpha. And then I was just thinking you correct the geodesics to order alpha and perturb it.
No, the problem is this. This is again what Shiraj was asking before in a different language, that is there a kind of a symmetry for which the Carter constant I understand? The good thing is that for circularity argument, I have an equation involving curvature. Okay, so I can use my field equation back and understand at what order this is violating or not. For geodesic, I don't have such conditions on which I can work. It's not clear how equation of motion, unless I know the space-time. So finding a diagnostic criteria, functions of the curvature, and then looking at the existence of Carter constant, we don't have that. This is the problem. Mathematically, it will be amazing we say that Carter constant exists if this curvature identity is true.
No, maybe I'm missing the point, sorry. I thought eventually what you care about for observational purposes are what are the geodesics.
Yes.
And the Carter constant helps, I thought, because it like separation helps you find those geodesics. But okay, let's assume you don't have a Carter constant. But you have this perturbative structure, the space-time. Is it so hard?
It is hard.
To find your correction.
It is hard. The geodesic, because once it does not separate.
Yeah.
Okay. In principle, one could use, actually, for shadow calculation, you could use what is called a numerical, shadow the tracing of light rays technique. So, but then it's making out of it with the observation is very difficult.
But this matter is unknown.
But here you don't require, it's just conditions, right? You don't have
Maybe
to.
that's the point, that you don't really know the solution.
Oh, you don't know the solution at all.
Even actually.
No,
These are all the stuff, general
Okay,
theorem.
but no, so maybe I got it wrong. I thought the point was that you're sort of interested in quasi-normal modes, etc. Because in the end, maybe all that last stage is blah blah. It's just a pure black hole, and maybe you get some insights from the geodesics and so on of the pure
But the
GRs.
problem
I
is,
thought that was the
we have not even a single general set rotating solution beyond this. We don't know anything.
in perturbation theory.
In perturbation, you know an order alpha.
Order-
But if you do perturbation, then it almost turns out everything will be circular, like everything will be very simple, like at least order alpha. That's not very interesting anymore.
Sandeep's question was, suppose, at least my understanding of his question is, that suppose you have a Kerr black hole,
Okay.
a genuine Kerr black hole, which is then perturbed. Then it will not be hard to,
Yeah.
you know, the
Perturbed by
geodesics Kerr, perturbed by alpha.
Okay, so people have found a solution which is order alpha. That solution has
You
been
find an order alpha solution, and then you can then find the order alpha
Oh, that has
connectivity.
been beaten to
Yeah,
death.
so that's-
That has been beaten to death.
Maybe that directly
That-
connects to quasi, no, you do
And-
something similar.
No, Sandeep, that has been
Okay,
beaten to
sorry,
death.
that's what I was trying to say.
Sorry, I listened then. That has been beaten to death. There are many class of this little bit perturbations and solutions, and all those parameters has been bounded by whatever observation you can find.
But maybe his point, I'm not sure, but maybe what he's heading towards is that because there's all this complicated matter in the middle, they're looking for some general structural properties of the
Yeah.
quasi-normal modes without knowing exactly what
I'm going to tell you what that general structure is. Good. So this is the whole point, that quasi-normal of final black hole may carry the signature of non-circular. Okay. But as we were saying, there is no non-circular exact black hole solution. So we need a kind of a phenomenological approach. You have to figure it out. If there is a violation of circularity, what is the generic signal we'll see? And then, again, I note that the circularity implies T phi isometric. If the circularity is broken, we expect the absence of this isometry. And what is the consequence of it?
And just to get it right, please go on. The Einstein branch would have circularity, as you show,
Only for,
but because of the matter, it's not clear.
no, I mean,
Is the
vacuum solutions of any EFT
will
will be circular in the EFT sense.
in the EFT sense. So either you'll have this non-circularity because you have another branch, or
Something
because of
crazy.
some matter effects. Is that-
Matter effects, or maybe there's a possibility that you can have scalar tensor theories, non-minimal coupling in the theories. The theorems assume there is no such thing.
It's
So
not
therefore-
just the kind of high
Or-
derivative correction you wrote, but extra stuff.
Stress of stuff, non-metricity.
Not
Non-metricity. The dynamics is
Also
not
is governed by other.
Sorry, there's some assumption on the matter. The matter also.
Obey certain, this, as I was showing you, this kind of assumptions is there. You started matter. This now what they show is that you can have scalar fields, EF field. If you start with GR, these assumptions are also valid in certain order. You have to look at exact one. But for vacuum, it is obviously true.
Very, very sorry, naive question. My understanding was that the final ring down, in these mergers, where you see the quasi-normal modes, that doesn't care much about accretion distance,
No.
because you're like
And it's an isolated black hole.
It's
These
an
are
isolated black
These
hole.
are not, at least for the LIGO black holes, are not the one which we have accretion. There are possibility of accretion depths in certain cases, but the one which we have seen. So therefore, these are clean signals.
So very clean signals, right? So
Okay. These will still kill me. Clean signal, why I mean is that I may be able to, because the SNR is very low. As a result, I will be able to see the fundamental mode, but overtones will be very difficult to see. So there is an ongoing debate in gravitational wave data analysis community that have we seen the overtones or not
in the quasi-normal.
in the quasi-normal mode by higher end modes.
Okay, but just before that, so therefore, to the extent maybe you want to probe changes in quasi-normal modes because of these departures, you're not so sensitive to whether this matter condition.
Not conditions, but so we expect it to be a circular path.
So therefore, the signals could only arise if it was a solution which was genuinely on another
branch
No.
or something crazy which you do not.
Okay, or this non-metricity scale.
Something crazy which we do not have. So therefore, it is important to test it.
Got it. Okay, thank you.
So the idea is this. So this is, I will not go into this mode. So basically, this is the time isometry, which gives you e to the power I omega t. Then there is a phase. That phase is very, very difficult piece. It depends where you truncate your gravitational wave signal. What do you mean by the beginning of the quasi-normal mode part? Okay. The data analyst has given us how to set this. These are all very, very hand-wavy, to be honest. Then there is this SLM, which are T theta phi. These are YLN generalization for Kerr. Okay.
Now you're looking at the late time.
Late time margin. What you show is that T phi isometry led to this kind of conditions on omega. So basically, omega ln. So if you look at these two sets of mode, okay, these are called polate and oblate mode. Their frequencies are related by these conditions. Think about that. This is like saying M2 minus and there is an isometry.
These are the ones rotating and
counter rotating, exactly. Okay. Now, you can create by hand, you can create a waveform solution which violates this isometry. Okay. So this would have been circular solution, and this would have been a non-circular solution where these two are different, and you can define their difference to be the non-circular parameter. Okay. Now, these are these different sets of modes. So there is this particular mode, the time which determines the envelope. Okay. So quasi-normal modes are the decaying envelope, right? There is the envelope, there is the oscillations. So those are constants.
How to make sense of that figure and
so this is what the spiral mode. This is where the things are revolving with each other. So in some sense, this is where you can think of the velocities are small. The characteristics velocity is small to the light speed. V by C, you can do order by order in calculation. This is what is called the PN, post-Newtonian. Then there is a part where voodoo takes place. So that means we don't know. Relativists don't know. Only the people in computer science knows. Okay. This is where the numerical relativity sets in. And then at the end, you have a single black hole and photon. And there where the Chandrasekhar sets in. Okay. You can do Visheshwara Chandrasekhar kind of calculation. So where you have a stationary black hole at the final state, or on the top of it, you are looking at fluctuations. So GAV plus HAV. And you look at the gravitational perturbation set. Technically, what you should do, you should start with the non-circular solution, look at the fluctuations, solve the fluctuation equations, write down gauge fixing conditions, but we cannot do that. We don't have such a solution. So what we do is that we create a waveform model.
Wait, sorry, what did not have a solution for?
We don't have any non-circular solutions. We should start.
Wait, you're looking at the
late part. Suppose, so what you are looking at, what is this test is? This test is to show whether the late black hole is non-circular or not.
You're saying since everything you can create is circular.
I mean, ideally, okay, there is a solution. There is something called ghost theories. GS to ST. I don't know how good these theories are. These theories are skeletons and kind of, for which there is a presumably a non-circular black hole solution. People have. I have not studied this paper. I just looked at it a few days ago. Then there are very, very interesting things. Okay, I'll tell you something interesting because we can always
if you do something which satisfies all sane energy conditions by adding matter.
This is those things, those kind of theories.
So those are sane
theories, but they are non-minimally covered.
Okay, that's fine, but not any kind of obvious.
No, there is no. At least I don't know whether the deeper things are there, but
Okay.
on the top of it.
Wait, sorry. So now this. In the end, your complete quasi-normal modes around the vacuum solution. Right?
Vacuum solutions. And they, by theorem, should not be circular. It should not be non-circular.
Yeah. So
therefore, what I'm doing is that I want to see if this is true observationally.
Yeah, no, I'm trying to understand this whatever scalar tensor, whatever you have. There also you're computing. If you imagine violating circularity, it's around the vacuum solution.
With vacuum solution, by vacuum means there is no other test matter. There is no other matter except the theory.
The background will be just pure gravity.
Pure gravity. But there, pure gravity means GAV and phi's testing because those are part of metrical simulation.
All the background. So not just GAV.
Not just GAV. Not pure GAV.
So there is no consistent truncation in that model to GAV.
GAV means? No, when there you have to include the dynamical degrees of freedom. It's like a Browns-Dickey theory. Browns-Dickey theory contains GAV and phi. So you have to.
And there's a linear coupling of phi
with the GAV.
Meaning, if you turn on GAV, that induces
phi. And here the coupling is more complicated.
That is a very unusual kind of thing, right? normal thing.
It's a model. It's a model for which there is a black hole solution which has non-dr/dt term which you cannot throw away. But
Complex such theories cannot have a positive stress tensor because
what?
Because
you have to be careful. How do you define stress tensor for non-minimal?
That's a poor man. I take derivative with respect to metric.
But then that will change the phi part also.
That's what I'm saying. If it's linear phi, I can do both sides.
But then the theorists will come back and haunt you saying that there is this Einstein frame versus Jordan frame. Which one is the correct frame to use?
No, but
people love their theory.
One of the miracles of string theory is that it allows it allows this coupling to linearly create gravity.
No
gravity with some other higher spin fields, and yet appears to be consistent.
This is the least miracle of string theory. There are other bigger miracles. So for me, general relativity coming out of it is a much more miracle.
But what I'm saying is that normal.
Sorry, Shraddha, if you have phi r coupling is what I was thinking.
Yeah. So any h times some stuff, linear in h times some stuff. Now, such couplings exist in the beta solution theorem.
Yeah.
Right? You scatter two.
But you show that it's such that.
Yeah.
It cannot be arbitrary in string theory, right?
Sorry, I said wrong. If phi times non-linear, you scatter two gravitons and it produces a higher spin thing.
Okay.
That exists.
Yeah, that's what I thought.
Yeah. Okay. Now, when that happens, it sort of seems like, because it's coupling to gravity is coupling to something non-linear, it seems like it's violating some sort of positivity of the coupling of gravity. Gravity normally couples to a positive energy, but it couples to a linear field that can go both sides. So you might think all hell would break loose, but string theory does not break.
Even higher spin theory, it could break through, right?
Yeah. And it's very unusual, right? I mean, you can prove that in any two-derivative theory of gravity.
This is the
impossible.
Reggie Poles.
Yeah, exactly. It's impossible for this to happen. There's just no, in any two-derivative theory of gravity, there's never a coupling which is linear in some other field and higher order gravity. So somehow.
But for me, it is there in capital R. When capital R, it just does not allow. So now the question is that, so you have this waveform model, you put it in your data, okay, and just do a what is the posterior of this? This is not an easy thing because you are doing multi-parameter posterior and you don't have a theory for it. Okay, so obviously now.
So you said that circular, non-circular solutions are not mean that you cannot write them down analytically, but theoretically maybe there are.
Believe me, it's very difficult. Numerically, even writing down curve, try to solve mathematics and get a curve solution. That itself is not that easy. Okay. No, there are certain solutions are known. Numerical solutions are known. The problem with numerical solution is that then the question is how to find the horizon. You have to do it everything numerically. It's not that easy. I can convince you later.
Can I say
very specific matter configuration, certain solution exists beyond curve.
Okay. Can I say what I'm told as an old man today when I make comments like that? You've not tried AI. We can obtain the Calabi-Yau manifolds metric. So this
I will not go up to
anywhere. I just said this is what I'm told.
Both Calabi-Yau and AI are beyond me. So okay.
Yeah, but just to see here, you have said if I'm right, n equal to 0. So
you can do n equal to 0.
That's the sensible
thing.
thing.
The problem is that you can, but then somebody would say, because the gravitational community is that then it's not a consistent computation because the claim is that there are overtone signal in the data.
Oh, so
therefore you should do.
But really, is that true? I thought
now I
where they said if you just
there
throw them away, you could.
There is this strong disagreement between different groups. Some will say that we have detected overtone. It also depends on how do you do the data analysis. But then my bets are off. I'm waiting, let them decide, and then they'll tell me I will like.
Because of course we are keeping all the ends. Then it's
therefore, we have to publish the results. So therefore, we put both the. Then okay,
that 0 was what there.
This is like n equal to 0. 2 to 0.
Right, that's what
NLM.
Yeah. So you're only
L. I don't have to go to L equal beyond L equal to 2. So gravitational waves are L equal to 2. M is
the M quantum.
And this n equal to 6. This is n is the overtone number.
I understand. So what I was saying was when you fitted, you set all the
It's wrong here. It should be. Right.
Oh, that's the higher. So you kept 2 or something.
That's all. So again,
so your main point is that there was a degeneracy which is now broken.
And then I create a model which has this alpha parameter or some parameter, alpha, sorry, some parameter. Now let me do a multi-parameter posterior analysis from that data and fit.
And roughly you're looking for breaking of degeneracy.
And I'll not find anything.
There was the oblated proline. They were not.
No, they were not degenerate in that. I don't use the word degeneracy just as an example. So, but this says that this two must be equal. This T5 says.
Yeah.
Now I don't make them equal.
They should be equal and opposite. That was the. Okay, I understand.
Now, so do not trust this. Okay, there are the problem is this. So, there is no theory. Look, I am estimating both the mass and the spin and this extra parameter directly from the data.
But why can't you just phenomenologically put a non-degeneracy parameter?
Oh, this is exactly, I hope I do. The problem is that it's very difficult to write a black hole solution, which is asymptotically flat, non-circular, no singularities everywhere on the horizon, up to the horizon. I tried, tested it, but it's not easy.
But I'm saying just at the level of data.
No, data, this is good enough for data. I mean, what I'm doing, because I don't need an exact solution, because I can always do multi-parameter.
No, but what I'm saying is that you're looking for what you're looking for is violation of degeneracy.
Yeah.
Let's not use the word degeneracy. I'm looking at the violations of this delta.
Of
So
circular.
what I can do is that from the data, I can figure it out the posterior of this curve, of this parameter.
But I think without a model, couldn't you just you have a clear feature in the data that you have a prediction for, right? What I'm calling degeneracy.
But the data itself is nothing but data. Now I have to impose a model on it because I want to do a Bayesian analysis.
I understand. So I'm wondering if you just take, you had two omegas that were equal or minus of each other, whatever. You take one to be omega plus delta.
But that is exactly what I'm doing. Exactly that I'm doing.
And so just go back. I'm so sorry.
Yeah.
This one. I mean, so here you have these two parameters.
So
right?
look-
Just so I understand. Delta omega
And they are zero means they are equal. And
Got it.
that's exactly what I'm doing.
and then in the next plot, just so I saw it, you were plotting delta.
So, I'm not showing all the code. I'm being a little bit dishonest. I am not showing you all the mass estimator and spin estimation. The reason I'm not showing you because what they are very correlated with this curves. Okay? So they are called triangle curves. So basically what is happening is that one realization of mass and spin estimation, I am telling you what is the posterior on this two parameter delta omega and delta.
Oh, okay, now it's.
So just to understand, I mean, the standard LIGO pipelines will give you mass, spin, etc. Right?
Yes, but then
Are you going to change those also?
because I don't have a theory.
Correct.
So what
I
I
use those.
I just no, I cannot use GR mass and spin estimation. That is the problem because this mass and spin estimations are obtained by assuming GR. Here I have to do it everything from hand. So what I have, I write down a model with mass and spin definition same as GR. I can do it because there is an order thing which helps me. I'm assuming the assumption here is that whatever is so first of all, it is not even clear this structure is be true once the non-circularity is broken.
And it's not even clear this is the structure.
Because we'll be able to define that probably will be true because there is a time independence.
What you say is something will decay.
Yeah, that will be true. Yeah, I would say that this structure should be.
But if now I'm so sorry, I was but I'm confused. If you want to estimate mass and spin and all, then how are you doing it? I mean,
No, what I do is that so I do a little bit trick. So what we assume, first of all, everything is GR. We do mass and spin estimation from GR, which already knew.
Okay.
Then we go back to the original model, put this man and GR thing,
Okay.
and try to correct it whether.
Okay, but then there is a model which is not what you showed us, if I'm right, which is some higher derivative in R correction, but which has got some matter and all.
Oh, this is by model. I only mean by hand. I write down a damped harmonic oscillator. That's the model. The model here means this.
No, that's for the quasi-normal book,
Yes.
for the mass and spin.
So what happens is that in this model, the mass and spin information is there here. Okay, in the amplitude. So by measuring these things, I use the GR equations to convert them into mass spin.
But mass and spin are just labels. How does it matter? You're just like
There is a matter. So, but the problem is that one has to be very careful because what it matters is that you have to tell. Suppose you are measuring. You say I get a a violation of GR up to at 3 sigma. Good. So you have got some delta not equal to 0. For a black hole of mass m1 and spin a1, it could be this is actually a GR black hole of mass m2 and a2 with delta equal to 0.
But how could that be? I thought the prediction was that two things are equal,
No.
not what their value is.
So this no. The value, what I'm measuring is delta.
Yeah, so that's the difference between two
Difference.
things that no matter what the mass and spin were, would be equal. Right? So if you see that as non-zero, it doesn't matter what mass and spin.
No, this could be just data analysis. Look, what is happening is that you may say, see, I am analyzing the data. That
Okay.
I am in a parameter space where, because
Are you comparing two different events?
no, there's only one similar.
One
single.
then I don't understand how if
You're saying that
non-zero-
it could be independent of the mass.
yeah, why
and
do you
spin.
care about the mass and spin?
Yeah, probably. Or
I mean, that's what I thought. That you would not care. Or if
Okay.
needed, you would take
No,
that.
there is something. I'll come back to it because it's not. There is some data analysis thing which I'm missing now. That you have to care of this marginal speed.
But at zeroth order, you want to
Zeroth
look at
order
a difference.
Hmm.
The difference persists no matter what the mass is.
Absolutely.
I think it could be 0 and GR,
GR.
no matter what the mass is. If you see a difference,
And-
you've got a violation.
I think the idea is that you cannot measure this exactly. The error distributions depend on the. I think something of that.
Okay, some data analysis.
That is the error distributions around it depends on what is your A and other methods. So if you want to make a prediction that the posterior is consistent with 0 up to 3 sigma, this bound would depend on what is the mass and spin estimations of that. So that's the problem.
But that's like a factor of 2 or 3 or something. There's some,
Oh, no.
some detail, right?
Well, but you have to give you the posterior. So it turns out greatly that the posterior is completely consistent with 0 up to what is called that within certain sigma.
It's just one classic. The index 1 here means you're looking at the first excited quasi-normal.
This is for the
Or
one
the lowest
one.
The lowest, which is where you expect the best.
You're saying great. Wouldn't it be more
Yes, and-
exciting to find a deviation? I mean, okay.
We love GR. Oh. So basically what it turns out, not only theoretically, the observation, also the systems for which we can do this data analysis completely consistent with some. Then there is theorem for light ray. So then I'm going to put this theorem, which I have given a talk before, so I'm not going to.
For some particular event, I would say only mass.
There's only 1 or 2 events for which we can really do this SNR analysis.
Otherwise, it's too low. Signal
It depends on
normal
quasi-normal modes is not that strong. Recently now, there are, for example, if it is a LISA, it is very interesting because for supermassive black holes, the quasi-normal mode signal will be very high. We'll be able to see more. That's hope. Always assuming LISA is funded, which we don't know. Probably too, because some satellites are already.
But not the third arm of LIGO, which is costing India 3,000 plus crores. I'm just saying that won't.
I hope, but this will not. No, that will not create the significance of the data, but that will give you more localization. Something else you can do.
I heard a rumor that roughly at the time third arm starts, the second arm may be shut.
Look, I'm on Zoom. I'm not going to comment anything. So then there is a theorem which I'm going to say. But now the question of basically what we have learned that the circularity extends in EFTs. Okay. Second, whether the light ring extends beyond general relativity or not. This I have given a detailed talk here, so I'll just quote the theorem. What you can prove here, this is with my student Rajesh, that any stationary axisymmetric asymptotically flat spacetime in 3+1 dimension, this can be extended with an ergo region. So nothing to do with black hole, ergo region. Must have at least light ring outside the light ring. You don't even need Einstein's equation to prove. Once you have ergo region, there will be at least one, and this is very easy to understand. Light rings requires the potential having maximum and minimum. Okay. Potential is like proportional to the matrix. Derivative of potential is like a maximum and minimum notation. So first derivative of matrix does not require Einstein's equation. But if you want to know whether the light ring is stable or unstable, you would require Einstein's equations or the field equations. So therefore, it's not very, not very surprising that this will be true.
Sorry, light ring is a circular.
Unstable. Okay, I should not use unstable, but circular null geodesy. For Kerr, it's only on the.
And usually it's unstable, right? Like,
No, it depends. If it's a black hole, it is always there is at least one unstable quantity. But if it is a non-black hole, now it is known that there will be stable relativity. And then that's very bad because that's like a bound state. So once you perturb it, the quasi-normal mode will stay. It will not decay. And you can show it leads to nonlinear instability.
So like for what like a neutron star? What do you mean not a black hole?
Boson star.
Boson star.
Okay, neutron star is too big.
Too big.
Okay. Okay. So a rotating compact object with origin must have a light train. Okay. And the proof is independent of the gravity, does not require any assumption about the energy conditions. Okay. So that's very good. Okay, so what you have shown, the second surprise can extend. Now what you can do is that, so this is where I have defined a light train. So origin, of course, the definition is GTT equal to 0. This is a stationary axisymmetric solution with only GT5, okay, therefore circular. Asymptotic flatness condition is imposed. And then I will not go into this detail because this is just how do you define the potential, because I have given a talk here. So basically, I will show that this theorem. But what is quite interesting, I must give, and this is a homework you can try, that if there is a horizon, there must be ergosphere. And this you can immediately see, if you have an asymptotic flatness, del T is time-like outside, del T is, convince yourself if this is a rotation, del T is space-like, and then obvious there will be ergosphere. Okay. So therefore, what it means is that once there is a black hole, there must be a light ring outside. So black hole horizons, either there will be ergosphere outside or the horizon itself is ergosphere.
Is part of this theorem the fact that the horizon is generated by DT, but wait, I mean it's with omega d5.
So
right?
So it's null with that.
Yeah.
So if you go through
There is an assumption, something called.
as to what the horizon is put in.
So this assumption is called what is called the theorem says is that suppose the event horizon exists and it's a stationary spacetime. Then the theorem says that it has to be a killing horizon. Any stationary event horizon must be a killing horizon. This is a non-trivial statement. Think of it that event horizon is defined with respect to global conditions, and killing horizon is defined with respect to local conditions. And Einstein's equation holds true. You can show every event horizon in a stationary spacetime must be a killing horizon. In that case, this will go through.
Okay, must be killing, but there's still the question which killing vector is needed,
Absolutely.
right?
So now you already have a time-like killing vector. So the two cases can arise. Either the time-like case will be tangent and normal. In that case, you can show there is no rotation because what will happen? Spacetime will be static. Otherwise, you can show that it will be a space-like on the horizon. This part is a little non-trivial. You have to convince yourself.
I mean, is it possible that the horizon is null by definition, I suppose, and the killing vector which is normal to it is d by dt? In which case, it would not be true that d by dt would be space-like.
No. So then you can show then it means there is no rotation and horizon itself is ergosphere. This is exactly what happens for short.
Right.
So
here
the claim is that if there is a horizon, there must be ergosphere. Either the ergosphere is outside the horizon or horizon
or
itself.
it is the okay. I'm so sorry. Okay, yeah.
if it carries angular momentum, right?
It's kind.
That in this case, I think you could probably show that as zero.
What you show is that basically KB equal to K. Basically, you can show the rotation two form vanishes. That's all.
Right.
In fact, in that case, you can also show the zeroth law will become a triviality. Static black hole zeroth law is again a triviality. You don't need all this machinery or wedge products and all those things. It's a triviality. So therefore, this is also so the existence of this structure, horizon, ergosphere, light ring, which we saw in Kerr, also generalizes to any theory. Okay. This structure is also true. So we showed that circularity, how one can generalize it. We showed that how this, what is this called, the light ring structure has been generalized. Now the question is that, what about axisymmetry? Okay. So what we have found that any stationary axisymmetric vacuum asymptotically, this should be flat. I don't know how it becomes glass. Black hole, so some spell check. Black hole solution of any general metric theory must be circular. At least one ergosphere outside the horizon, at least one light ring outside the horizon. This is a general structure. So what if we lift the assumption of axisymmetry? Is it obvious that any stationary black hole must be accessible. Okay. First, let's try to see what about a non-black hole. There is an old paper by Lingam, this is a Maryland relativist, okay, and this paper is not very well cited nowadays. Okay, so this shows that any stationary stellar configuration at thermodynamically, what it means is that there is no heat entropy production. Okay. And then it's a fluid. So that's the assumption that you can describe the star like fluid equation. So it's not rocks. I don't know rock is a fluid or not.
It's pressureless.
No, you don't need a special weather.
I mean, rock, like
Rock-
dust at least
Dust.
is fluid,
Yeah.
but it's pressureless.
It's more
I
simple.
don't know what rocks are. Look, rocks.
So star is definitely this assumption suitable. So the claim is that if you start with a stationary stellar configuration, the domain of outer communication must be axisymmetric.
Axisymmetric meaning.
Means there is a second killing vector. Space-like.
So this is violated in some solutions, right? I mean, maybe not 4 dimensions, maybe not flat space. This is a centaur set solution.
Oh, yeah. These are the only one killing vector black hole, but this requires probably ADS or higher dimensions. Helical killing vector solution.
So what is the thing there? That
There's some Santos, Oxford guy.
Yeah. You know, I mean, Cambridge.
Kevin, sir. Oh, I should be careful. Yeah.
Yeah, they kill you. No, roughly, you might think if you've got a planet moving around. Far from axis.
Yeah.
So in some sense, it's strange that things moving around are described
But
by.
somehow GR, well, and I tell you why it happens. It's quite interesting. Okay.
And but in GR, it becomes a killing vector, okay. But there are GR solutions where it doesn't happen. In suitability.
and they are black holes. They have
Black-
horizons.
There are the one helical black
You
hole,
might have thought that such a thing cannot settle down.
Yeah, exactly.
That it keep radiating.
but it does not.
Yeah, but it's somehow.
This is where it has no axis of separation.
No, there is no axis of separation.
Yeah.
But there is no delta. There's some
It's more
helical thing
In
is
some
there.
sense, more like a planet.
I have to-
going around. And that,
I only know the solution by abstract.
Horizon is stable
despite something.
I know the solution only by
I
abstract.
might have
So
thought it would radiate. That's.
no, it's a stationary solution.
know.
So it does not.
Then you might have thought intuitively that if something is moving around, it
It is some weird asymptotic.
It's a 5D story with
5 or even 6.
So that's a separate issue. That's a point. You can have black Saturn. You can have black Saturn, which is complicated.
It's just normal solution, but somehow, you make a bump and that bump moves around and it's okay. Right?
GR equations are crazy. But anyway, so the basically idea is that you start with the interior, which has this PAV, which is like everybody will agree. This PAV with some eta and zeta built in and some heat conduction built in. You write down the entropy production, which will be, of course, this term, and you know that if you want entropy production to 0, these are all positive definite. So you will have shear and expansion and heat conduction. So this is your condition for thermodynamic equilibrium. It will be then you can show remarkably that there exists a killing vector for this section, which is given by the 4 velocities of the fluid. This I didn't know before I looked at their data. So the idea is that once these conditions you can show whatever be the metric will always have this killing vector.
There's a theorem in fluid dynamics that says any equilibrium. So I'm saying forget gravity for a moment. There's a theorem in fluid dynamics that says that any stationary fluid solution has the velocity proportional to a killing vector.
Which is exactly what.
So that's what
it is. Yeah. No, I didn't know.
Yeah, it's a simple thing.
My lack of knowledge.
Okay.
So I was very surprised.
the killing.
And that
Velocity proportional.
and you show that proportional constant is exactly that temperature. The way you define it.
Yeah.
Beautiful. Now the claim is that you have an inside killing vector. Can you bring it out? Is there extension possible, satisfying all the Isabelle boundary conditions, such that it remains killing outside?
Bringing out.
But you extend it out, you have a differential equation by which this killing vector is matched to the outside and this guy shows it is possible. It shows that you can take this vector, use these equations to bring it outside. And obviously, why this equation has to be used? Because box phi equal to R is any killing vector which obeys. If you can extend this by this equation, it will be guaranteed it will be killing vector outside. Okay. And what they show that Einstein's vacuum equation shows that the extensions obey a certain kind of this equations, where this T alpha beta is this condition. And then you can use regularity conditions on the surface of the star, and there is something called Holmgren theorem for partial differential equation, show that at least in the neighborhood of the stellar surface, the only solution of this differential equation is Tn equal to 0. And then, which will imply, at least in the neighborhood, just outside the star, this guy is a killing vector. What is interesting is that killing vector from time line will become space line once it comes outside. And that you can show that by assuming what is called the analyticity of the domain of outer communication and asymptotic flatness. And you can show that killing vector exists everywhere corresponding to an x. So basically what happening is just outside the horizon you prove, then you demand that your spacetime is analytic, which means that you will be, the metrics are all entire function. You'll be always be able to write down order by order and get it out. And you can show order by order, this killing vector can be taken to infinity, and infinity matches with the Poincare killing vector for rotational symmetry, and therefore this satisfies the condition for x. So the proof is that you start with the stationary star, identify the killing vector inside, bring it out by using this condition, show that all Isabelle boundary conditions are true. So there is no irregularity on the surface, there is no divergence on the surface, and then you use analyticity to bring it to infinity, identify with the del phi. Once, so the domain of outer communication of stationary fluid star in thermodynamic equilibrium must be accessed. Yeah.
So this is spatiative for fluid plus GR
Yes.
combination,
Yes.
not fluid 1 and fluid 2 combination.
That's a very good question. You are already pre-guessing my ongoing project. Is it possible to do it for once I add second order transport coefficient? I'll tell you the answer in a month. Because one should be able to do it. Like, the question is to show, I don't know whether there's a killing vector or not. I hope it will be. My guess it will be.
It will.
That will be nice to see.
Shares probably done.
Another interesting thing would be, so another interesting thing is neutron star will have, for example, the non-abelian fluid, the strange fluids. Okay, those they are multi-component. You can, from the point of view of GR equations, they will be less multi-component fluid.
I guess the physics intuition is if you have no entropic production going on,
You should
must
say.
have settled down.
Settle down.
because,
Yeah.
there's no way to.
No. Yes.
Second law is.
And we can make that a little more precise because the entropy production is proportional to sigma square.
Absolutely.
So sigma must vanish.
Spanish.
That's a killing vector.
But what will be interesting to show, for example, if the fluids are interacting with each other, there is exchange of energy, but nevertheless, you can come up with certain conditions. That is very interesting. Then you can make comment on, for example, strange stars or neutron stars. That's interesting. Okay. Yeah, yes.
So you said that this link vector, when we bring it outside the star, it becomes space line.
Yeah.
But then it's like instead of being null, surface, but the star surface is.
So what happens is that it's really not a null. There's a difference. It's a second order differential equation solved. The first derivative cancels.
There is a jump.
Okay, maybe then.
Okay. Right?
No, you
Sorry.
must. But if you please excuse me after.
Oh, definitely. You know.
Thank
Yeah.
you.
So I'll go ahead. I'll just say that we have generalized this for, this is a paper which Nitesh and somewhere, we show that for Lovelock class, again, it will go through. Not only that, so basically the idea is that can you write down these equations in Lovelock and play with all the Hoglund's theory, that whether you can cast into it. Even if it's a non-Lovelock class, there is a bootstrap procedure kind of thing. So there is some conditions on some. Bootstrap procedure kind of thing, you can show that the uniqueness, and we will go to, there is some extra regularity conditions you require. Okay. So this is even for non-Lovelock class, this can go through. So basically you can show the vacuum exterior of stationary star. This is not EFT sense, by the way, this is a full proof, okay? That again will be axisymmetric even beyond GR. There is similar proof for black holes in GR. So this is because of Hollands and Wald. So let me quote that paper also. The idea is that you write down the effective field theory of black holes, effective field theory of gravity, with higher derivative terms, okay, or in more fancy language, higher derivative operators, okay. And then you expand the metric also in the same expansion, okay. What you show that the axisymmetry also holds order by order, exactly the way circular difference holds true. You cut up to certain order.
Order by order, what?
In curvature square. Curvature.
Oh, the alpha prime.
Alpha. No prime. And then you stop at alpha to the power n. The violation of axisymmetry can always be set into the next one. This is again. So what it shows, somehow this notion that there exists a killing vector, time-lag killing vector, implies an axisymmetric killing vector. Also, that's very interesting. So the idea, the result suggests that any diffeomorphism invariant theory of gravity, minimally coupled matter, vacuum exterior, or asymptotically flat stationary configuration must be axisymmetric. More than in the EFT sense, order by order, the exterior must be circular. If it is a black hole, there must be light ring outside the ergosphere. This would be a general feature of any stationary asymptotically flat black hole solution of a general metric theory of gravity. So the stationary domain of outer communication is axisymmetric, while linguistic type of coordinates will always exist, and horizon will imply ergosphere, will imply light ring. Any violation of this structure will imply something crazy going on. Okay, so that will be very interesting. You can test it, okay, because you don't want to say crazy is not going on. So how do you test it? Axisymmetric, violation of axisymmetry. That's difficult because once you don't have axisymmetry, you don't have conservation of angular momentum. Then the quasi-normal mode structure is non-trivial because there is no YLM structure anymore. So you have to figure it out. I don't know how to do it. One possibility again is actually look at degeneracies. Because M2 minus M degeneracy will be broken. This is something we are trying to model. But otherwise, there is this extreme mass ratio in spiral, a deep black hole with a small object rotating around it. This is a very good system because we will have very long, PN wave. So even if there's a small thing, you can
because it radiates extensively.
And not only that, if you wait for long, you can in data you can fold it, and very small effects you can enhance. Right. You can do classic. So the claim is that if there is some kind of violation of axisymmetry, at least in light ring structure, what will happen? Your light rings now don't have phi dot equal to 0 equation. So now the phi dot is non-zero. So how do you draw the shadow will depend on the impact parameter from which you are. See, your impact parameter is L by E. E is constant, L is not. So therefore, the contour of the shadow now depends on L from which the. So you can again try to see that is it possible to constrain it by random models and things. So these are excellent ideas, and this would be a very interesting test of what I call geometric gravity. This is something our groups are really trying to push. So no exact black hole solution, relativity is known, but we know a lot about the nature of solutions. So we expect vacuum black hole solutions to be excellent. And I already said these are, so I should say there are open problems. So we still don't know whether the separability of Hamilton-Jacobi equation transcends beyond relativity. This is something we don't know.
This is the Carter constant.
Carter constant. We know great about the general class of axisymmetric solution. I can write down by hand what is the most general class. But are there solutions of some theory? That will be very interesting to find. Okay, everything is a solution of a theory, but the question is with reasonable manner. Okay. The uniqueness of stationary vacuum solution is not extended to any other theory. This is the major gap in our understanding. For example, I have spherical black hole solutions of Gauss-Bonnet theory. I don't even know whether it's a unique spherical solution. That's an open problem. We don't know. We don't know whether the uniqueness of GR, uniqueness extend to nonlinear matter field. Why? Because the nonlinear matter field, I know violets, no hair travels. Young-Mill black holes can have Young-Mill hair. Okay, even for asymptotically flat. Born-in-field black holes, I don't know whether the spherically symmetric solutions is a unique solution. So it will be very interesting to see nonlinear matters. By nonlinear matter field, I mean matter fields which are.
You're saying Maxwell, you know.
Maxwell's I know. Young-Mill I know.
Interesting.
Because Young-Mill case, I know that there are solutions which can have extra hair.
Interesting.
So no hair theorem is highlighted. What about uniqueness theorem? We don't know this.
What's the result for Maxwell?
Maxwell's case does not highlight it. Only solution is short is an
What are the solutions that have extra hair with Young-Mills?
There is some paper by this guy, Bison or something, as a numerical solutions is known. And now I think born-in-field, there are exact solutions with born-in-field hair.
And you have some intuitive words for why do these solutions exist?
Okay, so that's simply because, if I understand correctly, this is because these matter fields are self-interacting in nature.
So they push up.
They push.
So that it's like
There is a possibility of a configuration outside.
roughly matter outside the self.
But then there are very interesting things. This hair cannot extend arbitrarily large.
Yeah, because
So
that would be
That would be yes. Even if hair exists, you can show hair will be bound also. There are other results also. But we don't know whether uniqueness theorem. Yeah.
You say that such solutions are not analytically known or only numerical relativity.
Even numerically, see, what I'm not looking for a solution. What I'm looking for is that, of course, for Young-Mill case, I think there is now a good enough understanding of the numerical solution. I don't know what analytic.
I think there are analytic solutions, maybe radius though.
Analytic solution.
Yeah.
Analytic solution.
I think Okuri and others worked out this.
Okay, so then I
which is
don't know.
basically the kind of thing you said.
Possible.
But it might be in ADS.
without charge. The black holes are charged.
Oh, they might be charged.
With
No,
charge,
even with charges.
it's easy to understand because the angles themselves are charged.
Okay.
And then this is the superlative kind of.
Okay, I'm not sure.
I don't know
But it was certainly analytic.
possible.
I
don't know
would be
this.
more surprised if it was
Without charge.
without charge.
Then, of course, what happens to QNM structure? All these things I have already listed. So something else I want to come back. Okay, we found there is a theorem that black holes implies light ray. Now, this theorem has been extended to ADS also. Okay. Now, what it means is that so now we know that horizon will imply a light ray even for asymptotically alien boundary. I think there is a holographic statement for this. Maybe there is a holographic way because the proof of this in GR is extremely complicated. Maybe there is a simpler proof
Sorry,
in
what was the
holographic.
question? I was floating out. Sorry.
So the idea is that if there is a horizon,
Uh-huh.
there must be a light ring.
Uh-huh.
This has been extended beyond beyond asymptotically flat boundary condition. You can, however, proof that horizon implies light ring for ADS boundary condition. If that is true, now what is a light ring? At least there are certain calculations which show that if there is a light ring in the bulk, and if you study box phi equal to 0 equation in that thing, go back to ADS boundary, look at the ratio of the normalizable mode by the non-normalizable mode, relate it to the green functions of the CFT, the standard ADS CFT dictionary. Such green function will have poles with very small imaginary.
Yeah, because it's stable, almost stable.
So these are some what is called a non-hydrodynamic stable long-lived mode. These are only done by case study. What this theorem seems to suggest, any strongly coupled CFT such that the holographic dual exists. If you look at the thermal coordinator, then we look at fluctuations of thermal state, and it has to be on a sphere because we know that n equal to 4 super Young-Mill does not have this property, but corresponding there is no light ring. Okay. For the black brains, there is no light ring. So it is not a counter example. Black brains, there is no light ring. So you can show the claim is that there must be always non-hydrodynamic long-lived modes.
And if what? If there is an ergosphere?
If the thermal state, because the black holes are thermal state for me.
But you need the existence of an ergosphere?
We don't need the existence of ergosphere. No, they exist always because
Not in ADS.
I don't need an ergosphere also because the proof is that in ADS you can show that horizon implies light ring. So my claim is that thermal state fluctuations, the correlated will always have a structure such that it will have a long-lived mode. It will be universally true, possibly, okay, I should be careful. It should be only true for strongly coupled CFT, for instance, duality holds true. I don't know.
And light ring was it wasn't important that it was stable or unstable. Right?
At least for this, it does not.
But I mean, it's
Maybe
going to be long enough if it's
wait,
stable.
it does. It does sign will determine stability.
It's more than just.
Yes.
Light rings are almost never stable.
No, for horizon, there is no never stable. They're always unstable. So they're always maximum of the potential.
Yeah.
They're always maximum.
Probably just falling.
Yeah,
So no, what happens is that so the potential always has this structure.
it may take a long time.
What is may take a long time?
Meaning, because there's a light ring, if you're a little bit inside, it will fall in.
Fall.
But it takes a long time.
No, but
From many,
inside,
many times.
it depends whether you from light ring, one should careful.
Just a little bit of
Fine tune, right?
Yeah.
You have to
Fine tune.
units.
But you have to be careful, Shiraj. From
light fine tune so that it's
light ring to ISCO, it will take a long time. Once you are in ISCO, you just fall.
Yeah, all I'm saying is something trivial. That since the light ring is infinitely long,
Yeah.
so
So
go near enough to it, it'll be long. And maybe you can see a same sign.
one could probably make the Lyopkov kind of comment on that. So this is a consequence. So this statement in CFT is a consequence of a classical theorem that all black holes with asymptotic areas asymptotic condition must have at least one photon sphere outside the horizon. Now play with that. I don't have a proof. This is again just a guess, but we are looking for counter examples. If you can give me counter example, I will withdraw my claim. Okay. For example, it's important that one could create a counter example for pure radius. So that means you are looking Hawking page transitions, also those things. I think pure radius is a bad example of that. There's a black hole.
Shiverdev's been wrote a few papers on
Yes, but
implications of light.
Yeah, but something different, not this.
Yeah, very interesting.
So my play. So I would like to know. I'm going to propose this. So if I am wrong, please do let me know. So my CFT is very weak. H bars are very small.
That sounds very interesting. Sounds very interesting.
So basically, the idea is that somehow the Kerr structure, not the Kerr black hole, seems to be true, even if it reasonably okay extensions of GR. If that happens, hopefully, at least numerically, we'll be able to AI will give us solution. Okay, something like that, among other things. That's all.
There's a picture of some two lines are T and phi and
This picture, yeah. So this is what is called. So this direction is a T direction. This is a phi direction. That defines a two plane. Okay. You can also define another two plane perpendicularity R and phi. So think of at one point I make these two planes perpendicular. Now remove. The independent need not be true. The coordinate lines will mix. In general, that is a true. Right? But the circular spacetimes are those for which this will not be true. These are subclass of. If that happens, you would be able to set this cross component to C.
and they can observe that there is only one mistake of.
So basically, what it happens is that the coordinate curves somehow don't talk to each other. So therefore, this cross component, there is a coordinate system in which the cross component. It's World 7 chapter, I think. Stationary solutions, generations of solutions, something like that. Very nice chapter.
Thanks, speaker again.
Thank you.